Welcome back. Today we want to look at position, velocity, and acceleration, and sort of combine what you've been doing in physics class with what you have in calculus class. So in physics class, you probably either used X or Y for position. So let's just assume it's X, right? So position might be X, and it's a function of time, all right? And then if you were to take the derivative with respect to time of X, we could say that's dx dt. You said, oh, that's V, okay, the velocity, okay? And that will also be a function of time. So you could call that V of t. And if you go ahead and take the derivative of that, that would be dv dt, all right? Well, what is that called? Well, that's called acceleration. That's the rate at which your velocity is changing. So if your position was in meters and your time was in second, velocity would be in meters per second. And then your acceleration is in meters per second, also known as meters per second squared. So the process of taking derivatives can take us from position to velocity to acceleration. Now, your textbook in math uses S for position. Okay, the reason why it uses S for position or displacement is this is your position along an arc, or along a path, maybe is a better way of saying that. And remember, S had been used for arc length. So as you move, you don't necessarily move along the x-axis in a straight line. So you might be moving along an arc, okay? And you would have a velocity and an acceleration relative to that arc that you're traveling on. So S is just a more general term, whereas X usually means horizontal motion and Y is usually vertical motion. X, Y, and S are all interchangeable for position, depending on the kind of motion you're looking at, okay? Now, if we can go from position to velocity to acceleration, so position to velocity to acceleration, we should be able to go the other way, okay? So we can go this way by taking the derivative with respect to time. Okay, now you can't ever go from position directly to acceleration. You have to go position to velocity to acceleration. Okay, now the acceleration, the derivative of acceleration has meaning. It's called jerk. When the acceleration changes very rapidly, it tends to jerk us. So if you run your car into a telephone pole, there will be a huge change in acceleration in that process. And so that's not very good for you. Now, we can go, as I said, the other way by taking antiderivatives. All right. So if we know the acceleration of an object, we could figure out its velocity, and likewise, from the velocity, we could figure out the position. Okay. We'll need to have a little bit more information, but we'll see that in the examples that come up. Okay. So anti-differentiation lets me go the other way. Now, unlike taking derivatives where there's meaning for going past acceleration, there really is no meaning for taking an antiderivative of position with respect to time. Okay, so let's now look at a couple of examples. Okay, so example one. Let's say that V of t is equal to, let's go with 10t minus 2. All right, where time is measured in seconds and velocity is in meters per second, let's say. I won't write all of that down, but a problem should indicate that, okay? Now, if part A was find A of t, and part B was find, we'll say X of t in this case, we'll pretend it's horizontal motion, we could do part A very quickly by taking a derivative. Okay, so for our solution for part A of t is equal to the derivative with respect to time of V of t And hopefully you can see very quickly, that's just 10. Okay, so this would be 10 meters per second squared according to our units, but I'll just write it 10. So this linear equation for velocity, let me grab my eraser there. This linear equation for velocity ends up giving us a constant acceleration. Now for part B, I need to find the antiderivative of v of t. All right, we'll have a symbol for that later, but I'm not going to introduce this now. So x of t would need to be a function whose derivative is 10t minus 2. So we would clearly need a t squared. And if I put a 5 in front of that, the derivative of 5t squared would be 10t, right? Then we would have to have a minus 2t because the derivative of 2t is 2. And then we would have to have an unknown constant tacked on. Okay, so that would be an expression for our position as a function of time. Now to define the constant, I could have in the problem said where x of 0 is equal to 0. If that were the case, when I put in 0 for time, I better end up at 0 position. Okay, so with this caveat thrown in, 0 better equal 5 times 0 minus 2 times 0 plus c. C is 0. And then the solution will end up being, that x of t is equal to just 5t squared minus 2t as the final answer. Okay, so there's one example. So notice for part A, we did the old thing. We took a derivative. And for part B, we did something new. We used, we anti-differentiated, okay? Or we can say later on, we took the antiderivative, right? Now, let me continue with another example. Minimize my little picture here. So, example 2. Let's say that a of t is equal to, we'll say t minus 1. Okay, so that's a of t. All right, and we are supposed to, let's say for part A, find v of t given, let's say that I'm not going to give you v of 0 this time. I'm going to say given that v of 4 is equal to, let's say 8. So that would be at a time of 4 seconds, the velocity is 8 meters per second. And then for part B, we want to find, we'll use x again. It could be y or s, given that x of, let's say that x of 2. So at 2 seconds, we are at a position of 10 meters. Okay, so we're going to have those extra pieces of information given to us. The givens will allow us to figure out which c value to put in. Okay, without those givens, there are an infinite number of possible answers. Okay, so here's a of t equals t minus 1. So let's work on our solution now. So here's the solution to this problem. For part A, v of t needs to be the antiderivative of a. So 1/2 t squared does have a derivative of t. We can say minus t because the derivative of t would be 1. So you can see that what I have so far, the derivative of this expression is t minus 1. I can put in a plus c to give the general answer to this question. Okay, so that gives me all possible answers. Now, we want to know, substitute in that v at 4 is equal to 8. Okay, so we put in 8 over here is 1/2 times 4 squared minus 4 plus c. Just real quickly, 16, oh, that is 8 minus 4 plus c. So c is 4. So an expression for velocity as a function of time would be 1/2 t squared minus t plus 4. So that is the answer to question A. Okay. Now we need to move along and answer B. So we'll need the antiderivative of this expression. So x of t, we're going up to t cubed, and we better have a 1/6. So when we multiply by the 3 and taking the derivative, that'll give us 1/2 again. And we'll return to 1/2 t squared if we take the derivative of that term. And then this should be 1/2 t squared, because the derivative of 1/2 t squared is t. So we can use that power rule that I had mentioned in the previous video, or to sort of guess your way. You know it has to be a t squared, and you need to put a 1/2 in front so that when you take the derivative, you'll just end up with a minus t. And then you'll have a plus 4t, and then we always tack on the constant, because this will give me all of the possible position equations that would have the given velocity. But now, to figure out which one it is, we're going to use that x2 is equal to 10. Okay, so I can say 10 is equal to 1/6 2 cubed minus 1/2 times 2 squared plus 4 times 2 plus c. So just quickly doing the arithmetic, that's 8/6 or 4/3, minus 1/2 times 2 squared is just 2, plus 8 plus c. Okay, so let me get this right. 10 minus 8 is 2, plus 2 is 4, minus 4/3 is equal to c. So that's 12/3 minus 4/3, or 8/3. So c is equal to 8/3. That would be meters. We're putting units on that. But now I can say x of t is equal to 1/6 t cubed minus 1/2 t squared plus 4t plus 8/3. So that would be an expression of position over time. Okay. Now you can see this allows us to work with accelerations that are more complicated than what you've had in physics class. So far in physics class, all of your accelerations have been constant accelerations. All right. This acceleration is a linear acceleration. So you can see that a linear acceleration gave us a quadratic velocity function and a cubic position function. Okay. The degree will go up too when we're working with polynomials and we're going from acceleration to velocity to position. All right. So if we're to turn around and take the derivatives, every time we take the derivative of a polynomial, its degree drops by 1. So these would be the functions that we're working with. Now, the final thing I want to do is go over, kind of get us back to physics class. Let's look at vertical motion. So if we throw an object in the air, okay, so if you throw an object upward, okay, there will be some y value, a starting y0. I'm going to just call that y0, okay? So at time 0 in physics, we call that y0 or y0. You pronounce that y N-A-U-G-T, naught, meaning nothing, okay? So y at time 0, and then we have some initial velocity, which in physics you called v0, okay, or v at time 0, and then we know that the acceleration is always negative g. All right, I say negative g because g is equal to 9.8 or 9.81, depending on how precise you want to be. G is the number 9.81 meters per second squared, or if you want to use feet per second squared, it's about 32 feet per second squared. But it's going to be downward. So we usually we'll put a negative sign on that. So this means we're assuming that up is the positive direction. Okay, so that will be a negative g there. So if we start with that, let's see what happens. All right, so if a of t is equal to negative g, then what's going to be true about the velocity? What's the antiderivative of that? Remember, g is a constant. Okay, so I need a velocity expression whose derivative will be negative g. And here it is. If you take the derivative of negative gt, remembering that g is a constant, not a function, we don't need a product rule here, you will end up with just negative g. The derivative of the constant is 0, so that actually works. But now we need to substitute. We know that v at time 0 is called v naught. So I can write in, okay, v naught is equal to negative g times 0 plus c. So what is the c value? C is v naught. So I can say, now I can say the velocity as a function of time must be equal to negative gt plus v naught. Now that probably doesn't look as familiar as rewriting it this way. V equals v naught minus gt. So this is the physics expression you saw when you were throwing something up in the air for the velocity, right? Now, if I want to get the y position, I'm going to have to take the antiderivative again, okay? So to get y, I take the antiderivative, all right? Now, v naught, remember, this is a constant, so the antiderivative of it will simply be v naught times t, okay? Since v naught is a constant, the derivative of a constant times t is just the constant, right? If this had been, 2t and you took the derivative with respect to time, it would just be a 2. So because it's the derivative with respect to time of v naught times t, where v naught is a number, it's just v naught. So that works. Now, once again, remembering that g is a constant, okay, we need to make the t go up a power. So that'll be a t squared. We need something in front of it so that when we take the derivative, we end up with gt. Okay, if I put a g here and I take the derivative will be 2gt. So if I throw another 1/2 in front, a factor of 1/2, now when I take the derivative of that term, I'll end up with minus gt. And we'll add on the constant to make it give all possible solutions. Now remember, we're looking for the solution where y at time 0 is equal to y naught. Okay, so substitute in, y naught is equal to v naught times 0 minus 1/2 g times 0 squared plus c. You can see the first two terms go away, and c must be y naught. Okay, so let's get back to the answer then. So y must equal v naught t minus 1/2 gt squared plus y naught. You're used to seeing it this way. Y naught plus v naught t minus 1/2 g t squared. So because the vertical acceleration is always constant in physics, we go right to these formulas. If we assume that a is equal to negative g, since it happens all of the time, you go right to the formula v equals v naught minus gt, and y equals y naught plus v naught t minus 1/2 gt squared. If we had more generically, if we had started with a is just equal to a, then we would end up with v instead of negative g. Wherever we have negative g, we could put an a value. We get the standard kinematics formulas. V equals v naught plus at, and you would end up with y equals y naught plus v naught t minus or plus 1/2 a t squared. And remember, it depends on which way the motion's going. Y could just as easily have been an X, or in the case of the textbooks, they'll call that S for your displacement along the arc. Okay, so that's a summary of position, velocity, and acceleration relationships, which should tie all of the calculus nicely into what you've been doing in physics class.